Welcome back. This is week 9 of inverse methods in heat transfer. In the last week, we looked at a brief introduction to machine learning and saw how machine learning could be essentially seen as a subset of inverse methods in general, specifically inverse methods that depend directly on data rather than on the physics. Now, so far, all the examples that we have been seeing are examples of what we would call regression. Now, machine learning has an additional thing that it is able to do, and we will discuss this in greater detail both this week as well as next week. But this is called classification. Okay, so that is basically the set of algorithms we'll be looking at in this week. We will also see this week sort of a transition from what takes us from linear or even simple nonlinear models to the models that we will discuss in the next couple of weeks, which are known as neural networks. Now, this natural transition comes via something called a classification algorithm. I discussed this briefly last week. So let's look at the topics that we'll be covering in this week. And I'll also tell you briefly how linear models with a small modification can start looking like neural networks. Okay. So the topics we'll be looking at this week are variants of gradient descent. When I mean variants, this has several technical meanings within the machine learning literature. I'll be looking at a very small version of this. By variants, I mean variants that look at modifications required for large data sets. So when I say large data sets, what I mean is that when you typically look at methods that we use, whether it was the normal equations method or whether it was Gauss-Newton, etc., all these methods, the examples we did in class during these lectures were all with very few data points, 5 or 6. Of course, that was meant to be for convenience. Even otherwise, typically, when we build a typical model on an inverse problem, the number of sensors is not very high, at least within heat transfer. However, when you have machine learning, you actually have a large, copious amounts of data. So in such cases, the simple gradient descent method that I covered earlier on in week 3 or 4 of this course, that's not sufficient. You have to do some variations within that, and we'll see this small variations within this in the next video. The next and the main topic of this week would be classification models. There is something called the logistic model, which is for binary classification. What is meant by that is, in case you want to decide something like cancer or no cancer, is this chip going to blow up or not, depending on what the amount of power we provide is. Such things are called binary classifications, this or that. Basically, it means 2 classes. Whereas multi-class or a categorical model means more than 2 classes. So we'll discuss these cases in greater detail later this week, these applications of machine learning. And I'll also mention how, once again, this is an example of inverse modeling. Now, finally, we will talk about why are neural networks required and why we can't stop with the basic simple regression models we looked at so far. And that is the plan for this week. Now, there is a universal machine learning process that you will notice within everything that we discussed this week. I had briefly mentioned this in the previous week also, but the basic ingredients of any ML model are these 4. Okay, so you get new machine learning algorithms by simply changing various portions of this recipe. Okay, so for the first is data representation, which I talked about a little bit in the last week, which is if you have an image, how do you represent it? If you have a number, a set of numbers, how do you represent it? And of course, the data set that we collected. This is one important ingredient of an ML algorithm. How you do this is an important ingredient. Next, of course, is a forward model, which is where we will focus on. Next, as you will see this time, is loss function. Typically, we used to use least square so far. for our objective function, but it will turn out that there are other loss functions like binary cross entropy is a loss function that we will discuss this week, or a general cross entropy, or what can be called categorical cross entropy. We will discuss that this week. Finally, of course, the optimization algorithm that we use. So we have seen at least a couple. We have seen Gauss-Newton. We have seen Liebenberg-Marquardt. We have also seen gradient descent. Okay, there are a few others that exist commonly within machine learning algorithms, but we will keep our focus on these because they are good enough for most of our purposes. Now, just a brief look ahead onto what I mean by a neural network and how it is related to the linear model that we have already seen. So you might already be sick and tired of the model on the left, but I want to show a new perspective on this model. So this is something that we had seen already. We have this simple model of y hat equal to w0 plus w1x. But this model is essentially a analytical or algebraic model. Okay. So let's call it that. Now, this picture is very central to what we will do later on in not the next week, but the week after that, which is called physics informed neural networks. So I want to introduce you to this concept right now, and then we will build upon this over the next couple of weeks. So this is an algebraic or an analytical model. This, on the other hand, the model that you see on the top is the same model, but this is a graphical, or let's say a pictorial representation of this model. Okay. So the important thing to remember is when I draw a picture, it's exactly the same as writing an algebraic expression, except this is easier for us to visualize. This is easier for us to compute with. So this is what we use for computation. This is typically what we use for visualization or understanding. Okay. Okay. So let's look at this model in a little bit of more detail. So when I say w0 plus w1x, I can say that 1 is one feature. Of course, it's a constant feature. And that feature, or this is, I will call this a so-called neuron. Neuron is nothing but a computational unit. There is a number sitting there, in this case 1. Now, this 1 is multiplied by w0 and it comes here. Similarly, this x is multiplied by w1 and comes here. And you sum it up. This simply is a summation. Okay. And the output, which we will call an activation, or you can call it output in this case, is y hat. So y hat equal to w0 plus w1 times x. That's all this picture is saying. Okay. But notice that's exactly what this expression is also saying. So the picture and this are one-to-one equivalent. Okay. So these are equivalent. Now let's come to a more complex picture like this. Okay. This, as it turns out, is a neural network model. And as we will see from later on this week, all models can be written in this pictorial format. All models that we will be using can be written in this pictorial model, pictorial format. And all models essentially that we will be discussing in the next few weeks are all special cases of neural networks. Okay, so one can think of a linear model as a special case of a neural network model. Okay, so let's come back here and let's say we have some numbers here, x1, x2. Let's say I had 5 inputs. Okay, or I had an input with of vector of size 5. Now, I can now think of this region feeding into some neuron. What this neuron means, etc., we will discuss later. But for now, just think of a calculation. where x1 is multiplied by w1, x2 is multiplied by w2, so on and so forth, and x5 is, let's say, multiplied by w5. Okay, this one. Now this here, I will say something like z equal to w1 x1 plus w2 x2 up till w5 x5. And that would be a linear output. Okay. Very simple. So you take all these inputs, multiply them with w1, w2, etc., and you get a linear output at the end. Now that looks like a very simple model. Now I could similarly say something like this. And let's call this Z2 would be, now you have another weight. So I'll call it something else. Let's say Q1 X1 plus Q2 X2 up till Q5 X5. That would be the output of this neuron. So similarly, you can now think of outputs from each one of these multiplied by different weights coming out from each one here. Repeat that, whatever output you get here multiplied by some other weights, you get some output here. As you can see, at the end, you are going to get some function of x1, x2, x3, x4, x5. But there will be a lot of parameters. W1, W2, W3, W4, W5, etc., etc. Now, all these basically are examples of neural networks, though proper neural networks have one more twist. I'll show you that. But as of now, all you need to imagine is that if I give some x1, x2, x3, x4, x5, even though there is a picture here, you know that if I give you all these parameters in the middle, you can get some number out from each one of these four. Okay. Now, this thing here in a neural network is called an input layer, as marked here. So this is an input layer. This thing here is called a hidden layer. And this thing here is called an output layer. This hidden layer, we don't know what it means, and I'll discuss this in more detail in the next week. But we really don't know what the meaning of these terms are. But we know these are just calculations. They are just internal calculations that we are doing. Remember, we always think of a neural network as having some input and having some output. And this thing here is a black box. It does some calculation, and we are just writing what this calculation is. In a neural network, however, unlike a linear model, where all you do is sum things up, you add one more thing. Okay, so for example, a neuron, that is the output here, has two steps. It has a linear step, which is exactly the same as a linear model. But after that, you run it through a nonlinearity. Okay. What is this nonlinearity? It is just a nonlinear operation. So suppose at the output of this step, you got something like 5. Okay, so let's say W1, W2, W3, W4, W5 are all equal to 1. And X1, X2, X3, X4, X5 are also equal to 1. So the output here will be Z equal to 5. And then what you give is not just 5, but a function of 5. Okay, or a function of Z. So you will give out G of 5. What is this function? A typical function is a function of this sort. Okay, so something like G of Z equal to 1 by 1 plus e power minus Z. So that's a complicated looking function. This is called a sigmoid function. I'll briefly explain the reason for the sigmoid, but we will see this in greater detail later this week also. So the reason for the sigmoid function is very simple. It was supposed to simulate what happens in the brain. So the idea is this. Imagine that you are seeing or you are sleeping. Okay, so you are sleeping and somebody is shaking you to wake up. Okay, so you are well lost within your dreams, and your brain, or at least a few neurons which are supposed to wake you up, are asleep. Now the person shakes. Now one model of you waking up is like this and straight here. That is asleep, awake. Now this is not a continuous or a smooth function, and later on, as you will see, as we have been doing for gradients, we need to differentiate. So we have a smoother model. The smoother model is like this: 0, 1. So that is this model. It is as if somebody shook. And after a certain amount of activation, you actually woke up. So this is also called an activation function. But basically, mathematically, all that activation function is on the simple linear model. Remember, if you had multiple inputs, all those would have added up to. On the simple linear model, all you do is you put a function of this sort. That's it. So you take a linear combination. So add all these up, come here, put some nonlinear function. Suppose that nonlinear function was z square, then g of z would have become 25. So 25 will come out rather than just 5 from here. Similarly, this could be another nonlinear function. This could be another nonlinear function. Put all these together, then again repeat. So all a neural network does is it takes some input, linear combination, nonlinearity, linear combination, nonlinearity, linear combination, nonlinearity, and you then have an output. Remarkably, this simple idea of chaining together linear operations and nonlinearity is good enough to do not only one task, but any task. So a typical type of task is make a prediction. So that would be a regression task. Regression tasks, but these we have seen so far. Okay, if temperature is such and such thing at these locations, what's the temperature in the middle? What's the heat flux in the middle? That's a regression task. But another task is a classification task. So if a neural network is good enough to do anything, it should be good enough to do classification also. Classification says cancer or cancer or no cancer, spam or not spam. Is this thermally safe or not? So you're designing a mobile or you're designing a chipset. Qualcomm will ask, is this thermally safe or not? So such tasks are called classification tasks, and we will see that as a prototype, you will start needing this sigmoid function in order to achieve this task, and a simple linear function is generally not sufficient for it. So we will start looking at these ideas later on this week. The primary purpose of this week is to naturally segue, to naturally move and smoothly move from a linear model to a neural network model. In the next video, I will show you why we need different variants of gradient descent in order for optimization. And after that, we'll start looking at this idea of a sigmoid. So I'll see you in the next video. Thank you.